Good evening, one and all. Welcome to the data science program. So far, we were discussing about the decision tree algorithm in the past sessions. So we are in a module that is called as machine learning, and in the machine learning, we are specifically looking at the supervised learning technique. Okay, so uh, the continuation of the decision tree leads to what is called as random forest. So the main topic of today's discussion will be based on the random forest, but the random forest actually is a subcategory under what is called as an ensemble learning. So let me give an introduction to the ensemble learning first, so that we'll understand what exactly is ensemble learning, so that even the ensemble learning, irrespective of which particular machine learning algorithm we study, we can actually incorporate a ensemble learning from. Okay, so let's start with the ensemble learning, and inside that we will be studying the random forest. Okay, so let's consider a particular scenario, right? Wherein, say, you are playing Kaun Barega Crorepati. Okay, and in that you have a question to which you don't know the answer. All right, so you know that you have options. You can take up several. So there are options like you can go for a phone a friend, or you can even ask for audience pool. Okay, so question is asked either to you can pass the question to your friend gives you an answer, you can use it. Otherwise, the next option will be you opt the what is it? It's called as the audience poll, knowledge of your crowd, right? So you can use it, right? So which is more preferred and why? Okay, it's an open question, so whatever you feel, please answer, or you can put your answer in the chat box as well. Okay, so if those are the two options available for you to take up when you don't know a question, right? Which one you prefer and why? Anybody? So you'll ask for audience poll, maybe, right? Okay, so you see, you will ask if the audience poll is asked, mostly everybody has some handheld device using which they can say that, okay, answer A is the, maybe A is the answer, B is the answer, C or D. Everybody will write, type or press, do something about that. So everyone's response is captured, okay, by the machine processes that and gives you a something like, okay, 60% of audience say that this is the answer, 20% say. So there is an aggregation that is happening among all those are present over there. So again, it's left to you whether to go with that or discard that. But most of the time, since I don't know the answer, I went to the audience poll. So definitely I have to take it, right? So maybe, so 60% of audience say that this is the answer, means you will go ahead with that and you say that, okay, then take that as an answer. All right. So whenever a complex question is posed, right, to, let us say, hundreds of knowledgeable people, you expect those who come to such, those who are the audience of such an event like the general knowledge quiz, right? You expect, right, most of them to be knowledgeable, right, in that field, because otherwise they will never come to that. So if I don't have any interest in the quiz, why will I attend such that? So few of them will be your supporters, okay, right? Other than that, whoever will come there, you are going, definitely going to expect that they are knowledgeable people. So the point is that whenever a complex question is posed to at least hundreds of knowledgeable people, right? You will definitely get a response and you can aggregate that response, right? And that aggregated result is always better than the the response you get from only one knowledgeable person. Okay, so this is what is true. That's why most of your answers, right, what I get here is it's saying that I'll go with the audience support open, the crowd's response, right? So this is the fundamental idea behind the ensemble learning. So what do you mean by ensemble learning? Instead of using a single classifier and showing a test question, okay, tell me whether this diagram is cat or dog. You should not ask only one classifier. Take 5 classifiers, take 10 classifiers, okay, 10 different classifiers or 10 classifiers of the same time left to you, right? We'll come to that at a later stage, but as of now we are trying to define what is ensemble learning, right? Our fundamental idea is that the example which I had given you, right? I have a question, I have a very complex question, right? In the quiz, I do, right? I go for an audience call. But at the same time, when I'm building a machine learning model, and I want to know that, right? I want to increase my accuracy, right? I don't want to make mistakes, right? This is something like if you have only one model and if the model makes mistake, your result directly goes into the wrong, right, side. So accuracy reduces. But instead of that, what if you ask 5 different models the same question? Tell me which is this animal. Is it dog? Is it cat? Right? Out of the 5, maybe 2 or 3 will say that, okay, this is that dog. Other 2 may say it is cat. You can decide, right? Go with the majority and you say, otherwise, out of the 5, 4 will say it is dog, 1 will say it is cat. Now you know what to do, correct? So that kind of, right, that kind of model building where you use different machine learning algorithms, uh, you pose a question, you train each one of them, and you definitely you test them, and during the final conclusion, right, you will choose, right, you will perform what is called as a voting among them, right? So such a system is what leads to the machine learning scheme that is called as a ensemble learning. All right, I'll write one very important point over here so that we can refer it, right, whenever you read it later. All right, so this is the point. The average response of crowd is always better than one single response. Okay, so this is the fundamental line, right? So this leads us to, okay, I'll write a short form for ensemble learning, that is EL. Okay, again, a hybridized technique under machine learning. Okay, so this is the key idea behind the EL. Okay, now go back to the decision tree, right? So decision tree is a single entity. We know the card algorithm will be used to uh, train a particular tree structure, right? Now what we can do here, you train different number of trees. Don't go with only one tree, go with different number of trees. Okay, but now you already know that if I use a particular data onto a uh, particular, in the sense my complete data set I use to train one tree, and I use the same data points to a different tree, right? Both will generate a similar tree structure. Both will ask the same question at the beginning. They will be deviated into 2 parts, true something, false something. Again, the false will be split it into true, false, etc. So you are going to get the same tree again and again. Will it be useful? No, it will not be useful. So what is the idea here? I want to get different trees now, right? So what I do, I don't give the same data. What I do, I pick the data into subcategories, sorry, into sub parts, random, right? I will split my data set into, maybe if I have 1000 samples in my data, right? What I do, I take 50 random, okay? Then the another 50, train another tree, third set of 50, train a third tree. Again, you will not give from the same class, you mix it up, okay? So randomize, mix it up, and take a subset, okay? So train different decision trees on a random subset of your training data. So definitely that gives you an idea that, okay, I'm going to get different number of trees, no, different trees, okay? Number you can decide. So, but how do you do the final prediction? Because anyway, training is over, and when the testing comes, you show your question to all the trees that you have created, right? Each of the trees will give you an answer, okay? Again, I want to do an aggregation, right? So you can take aggregation techniques, are several that are going to come at a later stage, but as of now, simply think that I'm going to perform an average, right? Out of 500 trees I created, right? Say 400 say that this is the answer, so mostly you can go with that, okay? So now you see, since you create multiple trees operated on random subsets of your training data, you are creating a forest now. Okay, so very simple, nothing new to learn, right? No new technique is going to be taught today, right? It's just the fundamental overall big picture of what is called as the random forest. So I'll come to the random forest, but before that, let's have a big have a overall look about ensemble learning and a specific type of ensemble learning first. Okay, so but before that, let me write the point which I just introduced you to, right? So we know what is the what is decision tree. Okay, so I'll write this as an example. Okay, so example, we know the decision trees, so we'll start with that. Train the different decision trees on random subsets of the training data, right? So create random subsets and train individually. Different trees you can create, and every tree you try to train it separately. Okay, that's maybe the point one under this category. And then what I'm going to do as a second step, maybe training is over, definitely the testing comes into picture. So make the final prediction. Make the final prediction as an average value that comes from all the okay, of all of the trees, right? So also I actually added here the point how the tree comes into picture, right? Since we have trained multiple decision trees, okay, multiple decision tree. So since you have, again, you will see that this number is not just 1, 2, 3, 5, 10, right? Normally, again, there is always a big question coming from my student side. How do you decide what is the number of trees that you need to grow? Okay, so again, initially I'll give you an answer, but this is something like not a specific case. So the number of trees that you are going to grow in your forest depends upon what is your data set. right? How complex is your question? And is it image data? Is it speech? Or is it something else? It depends on that basically. But on a general way is that you can go with a number like number of trees required equal to 1000. So something that acts like a standard. So again, if you are starting some new project, right, always it is suggested to go to the publications that happened on that particular topic in the most recent time, just to know that what exactly is the most recent work that has been done. If you see a decision tree, right, or the random forest that actually, right, has been used for that previous work, you will understand that, okay, how many trees they have used, so that you understand that, okay, that's the complexity because of which they have gone to 2000 trees. So maybe that gives you a number to you saying that, okay, this is where I will start with. Okay, then you will definitely make the modifications. You can go with 1500, 2500. Then still it is taking accuracy is not good, you can go to 3000 or make some modification. But how to start with? What's the number? What's that magic number I should look for? Right, the answer is like general way. If you don't have any idea, start with the 1000. Okay, but yes, normally that is not suggested. You are supposed to look at the various work that already have been carried out in that particular field, so that you get some more idea about that and refer to that and start from there. That's what is suggested. Okay, so since multiple decision trees have been trained on the random subsets of your data, this leads us to the concept which is called as the random forest. This is a upcoming algorithm, all right, under this case. Now, so before going to the random forest related concepts, we'll see, right, a specific type of ensemble learning. Again, ensemble learning is a huge topic, right? Don't just think that it's a small thing which we covered just before the random forest. It's actually a huge topic, right? Anyway, we will not be touching that in pretty much detail, because here itself we are covering up there. You can apply this to any algorithm that comes across in the whole course curriculum. You can use it to build a ensemble learning. Okay, but let me give an example, right? One of the very famous ensemble learning technique is called as the voting classifier. It's called as a voting classifier, right? It's a type of ensemble learning. That's why I said ensemble is too huge. So we'll just touch one of them. This gives us a pretty much more clear idea about what exactly is going to happen when I create multiple trees, and how do I club the result obtained after every tree provides you a classification result, right? How can you use it to get your actual answer? Final prediction, how can you decide, right? The aggregation techniques, right, again will be coming. All right, so the voting classifier is something like, let's
Sir,
go for a question.
sir,
Yeah, yes, Manish,
sir,
please go ahead.
sir, I have one small request. So can you scroll it a little upside for a minute?
Yeah, sure, sure. Okay, this is the starting.
Yes, sir. Scroll down little bit. Thank you, sir.
All right. Okay, so we were discussing about the voting classifier. I'm going to draw a simple diagram over here, which actually tells us how a voting classifier is going to work. Okay, so it's pretty much simple and very straightforward method. Let's look at a block diagram. Okay, so I have various data, right, for training, and out of which I'll take one of them. Okay, I'm going to call it as the data instance. Okay, it's one of your training data, right? So what I do, I'll give this particular training data to say n number of classifiers which I know how to put. For example, if you know whatever we have used earlier, maybe you have used a logistic regression, you know how to build a decision tree. Maybe I'll add one or two more. Maybe say you know how to build a Bayes classifier, NB classifier. Anyway, it's going to come in your curriculum up next after we go for SVN. We'll definitely touch that. Okay. So, but before that, let's see. Let us say that I want. I know how to build these classifiers. Okay. So let me write say the classifier. This is classifier number 1. I will also write classifier number 2 and classifier number 3. Let's say I know how to build them. Okay, I'll give this is classifier 1, classifier 2, okay, and classifier 3. All right, fine. Now this data instance what I have created, right, I'm going to pass that to all these classifiers, saying that I am making them to learn according to their own way, because each of the classifier has its own algorithm using which it actually can try to learn, or the training takes place according to that equation. Okay, so that's why we have this, right? So let us say that I have my data set contains binary classes, two classes like cat and dog. So maybe each of the classifier is going to give you a result. Okay, let me try to create the space for the result like this. Okay, each of the classifier says that, okay, let me say this result is after a training is over, I give a testing instance. Okay, this data instance now what you see on the screen is a testing data. Classifier is already learned and you are testing. So that data instance goes to each of the classifier. Classifier will tell that, okay, this belongs to class 0. Okay, this second classifier says that, okay, your testing sample belongs to class 1. Okay, and the next one says it belongs to class 1. All right, so it is up to you now. What do you do? So what happens if you take a vote, right? So vote says that the result is class 1. Voting classifier simply works in this fashion. You take multiple classifiers, you define multiple classifiers, and you once you have defined that, you train them, right? Individual algorithms, whatever a logistic regression is going to do, it will be used for training class 1. Sorry, classifier 1. Let me write some names over there. So maybe you use logistic regression. All right, so maybe this is a decision tree. Maybe the last one is SVM, which will be coming up next. All right, or even the any other algorithm such as KNN, okay, etc. Anything, that's fine. So what we do, we have trained each classifier according to its own algorithm, its own implementing its own equation, right? So you test, each one says one answer. This particular question belongs to class 0, class 1, class 0, etc. So finally you take up a vote. How did you take a vote, right? You saw, right, what is the highest vote share? So most of them are saying that class 1. So only one says class 0. So majority says class 1. So you can declare that as your answer. Okay. So very straightforward, very easy. Right. This is what is a simple, what you call voting. All right. Okay.
Please one time repeat it. I not understand.
Yeah.
Please one time repeat it. I
Yes,
not
yes,
understand.
Sure. No problem. You see, we have a testing data, right? So the data instance, what you see is a testing data, right? I am asking the testing data. I am passing the testing data to multiple classifiers. Okay. What do you mean by multiple classifiers? One can be logistic regression. That is classifier 1, right? Second could be a decision tree. Third one could be SVM, Navy base, KNN,
Yes.
anything that is present over. Okay. When a same question is asked for
Yes.
multiple, right? What do you call multiple classifiers? Each one gives their own answer. Correct? Now, out of the answers, what are the answers available here? You can see that. First one says it is class 0. Second one says your question answer is class 1. Third classifier says answer is class 1. Okay. If the question was dog or
Yes.
cat, first classifier says that it is dog. Second classifier says no, it is cat. Third classifier says it is cat. So what is your answer? You will say that you take a vote out of them. Out of 3,
Yes.
2 of them say it is cat. So your answer is cat. That's what is a vote.
Yes.
Okay, fine.
Okay.
So this is what is happening in a voting classifier. So
Thank you.
it's pretty much straightforward, pretty simple. I should know how to create individual classifiers now. Okay, out of which
Yes.
anyway, 2 of them we already have come across. It's pretty much straightforward. Others will also come into picture as the time progresses. We will see each one of them in detail. All right, fine. So now the voting classifier works in this fashion. Now I have a question. Do you see any problem here? If I do this is pretty much similar to our the audience poll, right? You think that there are so many classifiers available, right? They know how to answer A or B, but in such case, in that Kaun Banega Crorepati, you have 4 options. That's all. So it's not a binary classifier. It's a right multi-class. You ask a question, right? Everybody will tell that okay, they're according to their knowledge, they will classify the question into A, B, C, or D, and they will give you an answer. So what you did, there is an aggregation that is happening, and the result will be displayed on your screen saying that okay, 60% of the people say answer A, then remaining 10% say B, right? 20% say C, and remaining 10% say D. So 60 plus 40, total 100. Now it is left to you to do a voting. Voting actually has happened, and results are shown on the screen. You will simply say that okay, go with A because 60% say that. Same thing happened here, right? So there are only 2 classes in my example, right? So 66% said that this is cat. Okay, 33% said it is dog. So you will definitely take a vote and you say that class 1, maybe in my example, class 1 is cat. So that is your answer. All right. So voting works. How the voting works? It's the same thing, right? The voting, anywhere you have seen a vote, this is how the voting happens, right? So same thing we have implemented. Right. So anyway, I'll before asking a question, I'll say that whatever voting that we have applied over here, right? This is called as, right? This particular voting technical term comes into picture. This is called as the hard voting. All right. It's a hard voting technique. That indicates that since the word is hard, there has to be something else which is smooth. Okay, but before going there, I will ask you a question. Look at the, just a second. Yeah, look at this classifier structure I have written. And if I follow what is called as a hard voting, will there be any problem? Or have you faced any problem when you did a voting earlier? Or while analyzing the average of the whole country, the voting that happened for maybe the central election, right? Have you seen any problem? Have you seen any problem in terms of the vote share or something, right? Something related to that.
So
Something.
there may be chances of equal voting also.
Sorry, I couldn't hear you. Can you repeat?
So there may be chances of equal voting for each class.
Equal voting. Okay. So now you see, just to avoid that, we have created odd numbers.
Yes.
Okay. In this case, I try to avoid that. So I will always suggest you to use odd number of classifiers. That actually eliminates that one. If you, yes, what you told is right. If I take 4, 2 of them say it is class 0, 2 more say that class 1. So then I have a problem, right? I try to eliminate that completely by using odd number of classifiers. Yes, what you told is right. I already have overcome that. Okay. So always I suggest use odd number of classifiers here. That will solve the problem which you mentioned. Yes, that's a valid point. But as we know, we have solved that issue. Anything else? Any other problem? Right? I just gave an example of the voting system of our country. Right? It's not only there. Everywhere we will face something. something else. Okay, can you guess that, or it's actually a very practical issue, right? So anyway, I'm going to give with the numbers. I'll try to introduce that, but if you can guess that, it's well and good. Maybe you have faced that, maybe in the school elections or your college election or something else. Maybe you have faced such an issue, right? When we say that, okay, I'll take the majority of so many out of the all the votings, majority voted for someone. If you simply take that as your result, right, maybe there is some issue. But anyway, on a when you take the overall aggregation, there may be different perspectives. Somebody may say that, okay, if you simply take like this, not counting the votes obtained for each of the class, then there may be a problem, right? Maybe that's that gives you some hint. So take an example. Let's say there are 100 voters, or let's say 1000 voters. All right. So what you are doing, you are say the first class, right? So that's a classifier 1. So this is C1, there is classifier 2, and there is classifier 3. So we have 3 classifiers. So out of 1000 voters, according to the C1, right? Okay, let me write, this is the particular, right, let me slightly move it up so that I can get some space. Let's say that there are 1000 voters. Okay, so I will use the 2 classes in my data set. So the class number 1 is the dog, and the second class is a cat. So out of 1000 voters, right, according to the C1, maybe I say 900 votes for dog, and cat got remaining 100. So total is 1000. Okay, go further. This says 490 and 510. Okay, 490, 510. All right, so this is actually the vote share when you take the overall national average, right? Something like that. So it's like, for if you ask a single person, so normally what happened was that, right? So each classifier, I just look at this number, and this number is for 0. I declare that as class 0. I never considered these numbers. Okay, I just declared the winner, whoever is got the highest. I just never looked at the number. So that was my previous case, class 0, class 1, class 1. Okay, so class 0, class 1, class 1, class 0 for I'll just write the names over there so that you don't get confused at a later stage. So what is class 0? That is dog. Okay, class 1 is cat, class 1 is cat. So you declared cat as a winner, right? I asked the question, who is this, right? 2 classifiers said cat, 1 classifier said dog. Okay, but now you see, there has to be a confidence in the classifier. If you look very carefully, the classifier 1 is very confident that it is dog, because 900 is the score for dog, 100 is the score for cat. But look at the others, right? Look at the other classifier, 490, 510, very close. 490, 510, very close. Okay, now what you do, there is another way of doing aggregation. What you do, you take a first sum. So how much votes the dog class has got, and how much, what is the total vote the cat class has got. Again, this is something like, before declaring the winner, there are 2 parties, let's say, in a country's election, right? So what you did, you take up the vote that each of the candidate of a particular party gets from each of the assembly locations, right? What you do, you keep adding them up together. So that actually gives you a vote share, right? There is another way of declaring the winner, but anyway, that is not followed in our political elections, right? Anyway, you will never see that the vote share coming into picture. Simply say that, okay, he's in a constituency, somebody gets the highest vote, means he's the winner. Okay, so their numbers accumulate together to form a government, right? So anyway, this technique is not applicable over there, but still, right, this is pretty much valid. You understand why. So 900 plus 490 plus 490. Okay, so how much is that? 0, 8, 18, right? So this is the total weight shape of the dog. Then if you add the others together, so there's a 0, 1, 1, so totally this is 2, 11, 1, 1, 2, 0. If you use this kind of aggregation, who is the winner now? Definitely you see dog is a winner. Okay, so basically depends on what is your aggregation. So now I'll define the other one. Now you see it's actually a probabilistic way. Out of the total votes that has been casted, this is the 1880 divided by that number, right, is the chance that out of all the classifiers, they say that, okay, dog is a class. Similarly, if you use 1120 divided by the total number of the votes casted, right, you will say that this is the chance that the given image is cat, right? You can even use this technique. So this particular method is what is called as the soft, okay, soft voting. So ensemble learning using multiple classifiers. Out of ensemble learning, one of the easiest technique to understand is voting classifier. So I brought a voting classifier. Now you know what is a voting classifier. Inside the voting classifier, you have two options of aggregation. First one is a simple look at each of the classifiers result, right? If you have used normally odd numbers of classifiers will come into picture, right? And in the odd numbers, right, you will say that, okay, majority say that it's a this class, it's a you declare that as a winner. That's a hard voting. At the same time, you can do a probabilistic calculation by calculating something like a vote share, and you will give a result, right? That is called as a soft vote. Okay, do we have any doubts so far? All right, so let's move further. Yeah,
Hello, sir.
please go ahead.
So, sir, which one is I think give accurate results, sir? Like hard voting or like soft voting? Which is accurate?
No. The options are given there in such a way that you can decide what you. Okay, there is no accuracy because it's a perspective, right? Now you see, as I give an example, the political parties will never go for the soft voting part. They say that I want the hard voting because they want to get a larger number. Okay, so but if you want the vote based, actual vote share based result, then you have to go for soft voting. So there, I cannot say that this is better or the other one better. There are, you have to take it like you have two options. You can choose any one. Okay, so most of the time it depends upon what accuracy you want to achieve, right? Most of the time the soft voting is what is preferred, I can say, but that may not give you the highest accuracy, right? Most accuracy comes from the hard this thing, but as I told, right, it depends upon what type of algorithm you want to use and what type of results you expect, right? So soft voting in the sense probabilistic way. If you want to deal something probabilistically, you can go for the soft voting. Okay, hard voting is a straightforward answer. Majority results you take up and you give it as an answer. So more accuracy comes from the hard voting case. Okay.
Okay. And also like result depend upon the voter category also, sir.
Voter category in the sense how many number of classes?
No. Suppose like age group. Suppose some image is there like cat and like a dog. Maybe child will not able to identify clearly. Correct. Difference between both.
Yes. Correct. That's a factor. Perfect. Okay. Do we have any other question? Okay. Now let's take up another example. All right. So this actually gives us another perspective. How and this ensemble, why the ensemble works very fun. Okay, why not only single classifier? When you use multiple classifiers and you try to build an ensemble out of it, why that works pretty much fine. I'll try to give you a big picture of it. Let's take up another example. All right, so let us say that we have okay, I'll write first. Consider a biased coin. Okay, what do you mean by unbiased coin? Means when you toss a coin, equal chances of getting head or tail. Let us say there is a biased coin which is going to give you more number of heads than the tail. So probability of getting head is slightly more. Okay, 0.51. Okay, when I say 0.51, you will definitely understand that then the probability of tail will be 0.49 because only two options will exist. Right, now let us start doing an experiment. All right, in my experiment, the first stage of experiment is simply tossing the coin once. Okay, you may get head or tail. Correct, I have tossed the coin only once, and out of the two results, one of them will come. So definitely you say that it is 0.5. I don't see a 0.51 coming into picture. Okay, doesn't matter whichever you get. You may get head, you may get tail. Your answer is same. If I ask a question after tossing this biased coin once, right, you will say that yes, the probability of head is 0.5, or if you got a tail, you will say that probability of getting a tail is 0.5. All right, okay, that's the first step. All right, I'll just write toss once. You will definitely observe that probability of the head equal to the probability of the tail. Finish. Experiment number 1 is over. Next, toss 100 times. Right? Since there is a bias, right, you will be able to observe that bias. Okay, so it will be right, p of h will be 51. Let's stick the ideal case, that is definitely 51 for head and 49 for tail. You will observe a slight difference, and let us say it's very negligible because they're very close. Okay, experiment number 2 is over. Go to experiment number 3 using the same thing, right? I want you to toss 10,000 times. What do you expect? Out of 10,000, heads will be 5,100 and the tails will be 4,900. Now you see there is a large difference coming into picture. Okay, so as the number of times you repeat this, right, because of the bias, right, you will observe that there is a gap between the number of heads you get and number of tails you get. All right, why I gave you this example? Because the ensemble technique which we have defined, right, that works on the same fashion. So whatever looks very close, if you repeat it lesser number of times, I don't see a difference. Okay, but if you increase that, right, if you increase the number of, in the sense, number of experiments, right, the number of times you are going to repeat that, if you increase that, you will see a clearer differences between them. So the point is that instead of using 1, 2, 5, 10 trees, if you go for 1,000 trees, right, that the result is evident in front of you, right? So you will be able to see, right, you will be able to see that very clearly. Okay, I'll write one point here, right? So overall conclusion from this particular experiment is, right, about the ensemble. So the ensemble works in a very similar fashion. Okay, so what is that very similar fashion? I'll just write few more points here. That is, so if several classifiers have an accuracy slightly better than the random guessing, right? So you see, I should not pick up something at random and ask them to guess. So let us assume that there are several classifiers, okay, that have an accuracy slightly better than your random guess. Right. So what happens? The majority vote of the ensemble, right, with the sufficiently large number of members will definitely, it's again, I'm going to give you a mathematical a rule, right? I'll write it afterwards. But I think you have already studied that in basic mathematics somewhere, right? It already has come up, right? You will remember that name when I write it. Okay. So the point is this: ensemble works in this way. What is that? So it says if the several classifiers have an accuracy slightly better than random guessing. So what is that slightly better way? You see here, right? 0.51 and 0.49. 0.51 is better. But don't use it only once. Repeat it how many times? 10,000 times. What happens? That better 0.51 becomes 5,100. The one which has lesser value will be, you will get a huge difference among them. So that you can say that, okay, 51, whoever is getting 5,100 is your result. Okay. So that's our approach. Okay, so that's ensemble learning. I'll write another point under this. So the majority vote of the ensemble with sufficient ensemble members always approach, oh sorry, spelling mistake, always approach 75% or better. Right now you will ask a question, how can you say that 75%? That's why I told this comes from, this is a proven fact. Okay, I'm not saying this, or even I cannot do the maths and show the result over here. This is a proved mathematical concept that is called as, right, the theory of large numbers. Okay, so that's a mathematical concept wherein you come across all things. All right. So instead of picking up randomly, take up the ones which, though they have marginally closer result, take that and repeat it for a large number of times, like 10,000, 50,000, or 1 lakh, something like that. In such cases, you get a result. Maybe you can take an aggregation of the result to say that which is better, like yes or no, like that. So that comes under the theory of large number, or it is also called as law of large numbers in math. So you want to explore more on that, please use this particular keyword for your search. You will get a complete details of that. Okay, so we will be not touching the law of large numbers, but our overall idea is that how ensemble works, what is ensemble, and how the one of the part of the ensemble is the voting classifier, and the simple working of a voting classifier using soft voting as well as hard voting. So this is what it's a overall outline we have been discussing so far. All right, do we have any questions? Okay.
Sir, I have
Yeah.
one small question. Sir.
Yes, yes, go
Sir,
ahead, Manish.
Sir, what is soft voting, sir? Can you please throw some light on it again?
Yeah, definitely. All right, let me go back to answer that question. So hard voting is very straightforward. Whoever out of the 3 classifier, whoever gets the maximum votes, like cat is given by 2 of them, only one of them says dog, you declare cat as a winner. Okay, the soft voting comes into picture, wherein you count the number of votes each of the classifier has got. So let's say I tested for class A, right? That's 900 of them were assigned to the dog, 100 of them assigned to the cat. Okay, this is something like in a particular region in a country, right? 900 people voted for a particular party, 100 voted for other party, like that. So the second classifier, 490 and 510 is the vote share. Third one, again 490 and 510. Okay, now according to the winner perspective, right? Who is the winner? If you ask who is the winner, here this is the winner, this is the winner, this is the winner. So the hard voting worked in such a way that, okay, just counted the winners, right? So 2 of them said that cat, only 1 of them said that dog, so cat is the winner. That's a hard voting. Now what happens in the soft voting? The soft voting actually calculates the vote share. Sorry, let me go back. All right. So the soft voting actually works on the vote share, right? It actually counts how many votes the dog class got. 490 plus 490 plus 900, 1880. Okay. It also calculates what's the vote share of the cat. So 100 plus 510 plus 510, that is this. Out of the total votes, right, casted, you see dog actually has got 1880. The cat got very less, right? But since the principle used in the hard voting, that I am not worrying about how much vote you got. I just say that who is the winner. Majority of them saying that this is the winner, I declare them as a winner. So you said that class 1 as a winner, cat was a winner over there. But now you see the soft voting actually counts the number of votes each class has got. So according to that, soft voting will declare that dog is the winner. Okay. That's about the soft voting. Is it okay? Any other doubt?
With the example, can you tell me over here, like?
No, I told you the example only, right? This is the example.
No. So this I got like below this. Yeah,
Sorry?
so considering these things, sir.
No, this is not example. This is the next concept. Okay.
Okay.
Not
So
an
can you
example.
please?
This is not
So
example.
can you please tell about this example?
No, I just told, right? See, repeating everything will take a lot of time. I don't want to waste that. If you have any specific doubt in this, please go ahead. I will answer. Okay. Because if I start with this, I have to explain everything once again until the end, right? So just 1 minute back, I explained. Do you have any doubt in this? Right? Anyway, still I'll go very brief. So if you toss a coin once, a biased coin, right? You don't see any difference. They are pretty much close. Okay. If you repeat 100 times, you will see a difference. If you repeat 10,000 times, you will see larger difference. Okay. Fine. Now what happens? That is what is the fundamental idea behind the ensemble learning. Ensemble learning works. If you use only once, you don't see a difference. You use 10, little bit difference. You use 1,000, you see the clear difference. All right. So this concept is what has been already explained in what is called as the theory of large numbers, which is a mathematical concept. So in order to look at the maths behind all these concepts, I want you to refer what is called as theory of large numbers, or it is also called as law of large numbers. Okay, that actually tells, right, in pretty much detail, right, about this whole concept. But the fundamental idea is that ensemble learning works on the principle that you have to use large number of classifiers, not just 1, 2, or 10. That's why initially I told, if somebody asks me how many number of trees I am going to use in my random forest, I'll say 1,000. That's a good number to start if you don't have any idea. Okay. Any other doubt?
Right,
Sure.
sir. Thank you so much, sir. Thank you so much.
Sure. Please go ahead. Any other question? Okay, so I'll give some of the fundamental instructions that we'll use in the SK. All right, so that is voting classifier in SK. So if you want to implement, normally what we do, the first part will be you will be importing, right? You have to import, right? I'll show you the importing part for the random forest, as well as I want I want to show you the voting classifier. Both of them, let's try to bring. So normally you will see this part of the code. So that is from sklearn dot ensemble. You see, the random forest is not present in sklearn, any other part of sklearn. It is present inside ensemble because, as I told, decision tree is a basic algorithm. You repeat trees many times to create a forest. So that actually is an ensemble, correct? So sklearn dot ensemble you will import. All right. So you will import the random. I think forest F is capital according to the rule. Okay. Random forest, again C is capital. All right. C is capital. Same thing, right? You will repeat. Again, this is from the same. From the sklearn ensemble, you import what is called as the voting. Voting classifier. Okay. In addition to this, you can even bring, let us say, okay, let me bring the other one, right? So that is again not from the ensemble. This is from sklearn dot linear, which is the one which we have studied under linear. Import logistic regression. All right, then I'll bring one more. Okay, let me go with only three because sorry, we have random forest, logistic regression, and okay, let me bring one more. Right, from sklearn dot svm is present in svm itself. Okay, svm import what is called as svc. Svc for support vector classifier. Support vector machine is a concept. All right, anyway, we'll touch that towards the end of this particular module. All right. Okay, so we have imported three classifiers and one hybrid classifier called ensemble classifier, that is called as a voting classifier. All right, then normally we create an instance of that by whatever name you want. I'll define that as, say, CLF1, or okay, let me make the name very clear so that you will not get any doubt about the names given. So let me type, this is the logistics. So I'll call log classification function, CLF, is equal to, how do you instantiate? This is logistic regression. All right, so just remember the flow still remains same. Then I create another one. Okay, so that is random forest. So RF underscore CLF, that is equal to simply a random forest classifier. All right, then support vector machine. So I'll write svm underscore CLF, that is equal to svc. Right, so we actually have done the declaration that I'm going to use VC, and the names referred are log CLF, RF CLF, and the SVM CLF. Okay, now you are going for a voting classifier. All right, so how do you go with the voting classifier? It's very simple. So I'll give a name, voting underscore CLF. Again, you need to instantiate. So that is voting classifiers. Okay, I think we have capital. this is voting classifier, but you see, I need to specify what are the various classifiers I'm going to use inside this voting class. Okay, so I will use the keyword is estimator. Okay, estimators equal to, you create a list. Okay, inside the list you will write, so this is LR for logistic regression. What is your function name? You will write after that. That is logistic CLF. Come, then what comes next? I use another thing, so that is RF for random forest. Random forest according to you is RF underscore CLF. So RF underscore CLF you can see here, right? This is the one which I am referring here. Okay, RF underscore CLF. Okay, that is done. I'll use odd numbers as I told, so I'll go with the another one. So that is I think SVC is the support vector classifier. According to the names you have created, this is SVM underscore CLF. In the sense, this is the function which is supposed to be used. So I'll close this. That closes here, and I have created this. I'll close that. Okay, and one more thing, you have an option to specify what type of voting you want. So you can write that voting equal to, so you can specify hard or soft over here. Okay, so close it, the main bracket closes over here, and yes, you can go ahead with voting classifier dot, which is a function used, if you remember, fit. So fit function fits that. So if you have x comma y or x train comma y train already created, right? You might have already used the train test split function to create this, and it goes in the same fashion. Okay, so this is a main part of the code, right? If you try to remember, irrespective of which type of machine learning scheme is being implemented in the scikit-learn, this is the same flow. Instantiate, create an instance of that, and fit, and then go for a predict one. Okay, anyway, I'm not going to show the predict here. It's the same code like here. So this particular function, voting underscore CLF dot predict, which one you want to predict, you pass that. That is X test. So the result comes into picture, and you can make a comparison to get your accuracy score or any performance measure that you want to look at. It still remains same. All of them are pretty much same. Okay, so overall picture of the code will be something very similar to this. Okay, yes, any doubt with the coding part? Anyway, we'll write the coding. We'll definitely do the coding of this, and we'll explore more practically at a later stage. But before that, if you have any question, please go ahead.
Sir, could you repeat the last line, sir? X train, Y train.
Okay, so this is a training part. All right, so how do you train? If you remember, irrespective of whichever is the method that you are following, right, you will do a fitting, right? So this is the fitting part. Okay, so first I do the fitting in the sense, this is my model, right? Voting classifier. I have to tell that this is the, if a training happens in such a way that training data and the corresponding y value I have to pass. So how do you do that? X train is my training data, y is the correct answer for that. So I'll pass them, and machine learns. Okay, so the learning happens inside this particular line of code. And if you want to do, after this training, if you want to go for a testing, you will use a function called as predict. Okay, so voting CLF dot predict, you have to ask a question, right? Predict of your X test. So there will be 4 parameters. If you remember our previous codes, we use a train test split function for my data set that will divide my divide my complete data set into training and testing data. Okay, so train test split will be done. So it will split it into X train, X test, Y train, Y test. So out of which I'm using X train and Y train to fit the curve. But this is something like I'm teaching, right? If this is a question, this is the answer. X train is a question, Y train is the answer. I am teaching. But in a test, right, I'm not going to give the answer. I just give the questions to you. That is, for a prediction part, I'm just going to give you the X test only. X test is my question. Okay, you will give an answer. So that answer I'm going to compare with the correct answer to say that what is your accuracy. Okay, so that is what is going to happen after this. Anyway, during the actual coding, we'll write that also. But since that already has been done in several previous what you call algorithms, I'm not writing here. Okay, but definitely we have to do that when we do the coding part, right? Just remember that after the after the training part, there is a testing part, and calculating the accuracy also comes into picture. Okay.
Okay. Okay.
Sure. Yeah. Do we have any other doubt? Right. So this is a ensemble learning, specifically the voting classifier. But in general, I would like to give some points so that whenever you are going to build an ensembled classifier, right, by your own, you should remember these points. Okay, so these are some points which are important to remember whenever you use the ensemble learning. All right. So for of ensemble learning, you may have to, again, this is an observed fact, that's all, right? Again, I may not be able to prove it by doing some maths for you. Okay, so what happens, what is expected is that the various estimators or actually the classifiers must be independent. So result of one classifier has nothing to do with the other classifier which you use in the ensemble. This is what is the meaning of this point. Okay. Right. Again, whenever the predictors are used, you know that there are various types of errors that are possible, right? So all of them should not make the same type of error. That's what is the point, right? So different types of error have to be right. There will be error. So if you see very carefully, the previous example which I had given over there, though there is a what you call there is a winner declared saying that okay, the test data is cat. No one is 100% confident, correct? No one, none of the classifiers say that yes, your image is 100% cat. Nobody says. So normally what we people think, right, in machine learning is that I have built a classifier and I am doing a testing, and during the testing the result is a correct answer. Let's say I gave a cat as a question and the machine said cat as answer. Normally what I think is that my machine is 100% confident. No, never. In none of the classifier that happens. Always you see that, right? Something like that example, 510 out of total 1000, right? Or something like that. So, or maybe in even a better case, like 80 out of 1000, 800 out of 1000. Something like that will happen. Always probabilistic. Everything is probabilistic. So when these kind of errors, probabilistic way of making error comes into picture, you don't want each and every algorithm that you are using inside an ensemble to do the same mistake. If everything does the same mistake, there is no meaning in using ensemble. Ensemble is a probabilistic way. That's why I say, right, you use multiple classifiers. Each classifier should not do the same mistake. There should be variety in terms of the mistake they perform. Okay, so that's why I'm writing second point. Okay, so all the predictors. So these are the different words: estimator, classifier, product, predictors, all are same. Okay, must must make different errors, right? Then already we wrote that independent as possible, right? In a sense, independent, you can, one of the best way to make them independent is that you, whatever training data you give for one of the classifier, don't give the same data for other classifier, because learning is completely different. In such case, learning becomes completely different. Okay, so you you have a data set, create a subset of the data, give it to the machine, right? Another subset of the data, give it to the second machine. Another third subset of the data, give it to the third machine or third algorithm, and so on. Repeat this. Okay, so that is very important.
Excuse me, sir.
Yes, go ahead, Ruchi. We cannot hear you. I think your audio is muted. Ruchi, can you?
Just a minute, sir.
Yeah, sure.
Sir, so now I am audible?
Yes. Now
Okay.
you are audible. Can you?
Sir, in our code, we are using all the classifier in a single code and we are not mentioning any different data for them. Then how we will make them independent?
Yeah, so the voting classifier, right?
Yes, sir.
When you go back, you see here, only in the voting classifier we are interested in doing this. Okay, voting classifier is a ensemble. So inside the voting classifier, it is done. Okay, so default way is that now I am coming next. Okay, whatever we are going to discuss next will help you out in understanding how this data part is taken care of. Okay,
Okay,
so
sir. Okay.
what happens is that there is a concept called as in what all ways you can create the subset of your data. Okay, so just now I said that I just introduced the concept saying that, okay, you have to do a subset of the data. You should not give the same data to all the trees that are present inside your random forest. Okay, so that is what is going to happen in the next part that I'm going to discuss now. There you will get your answer. Okay.
Okay, sir.
Sure.
Okay, thank you, sir.
Sure. Okay, so I'll just write a point about that subset of the data. So we can train the models with different subset of the data. Now, again, in that case, somebody will definitely ask a question now saying that if in such case, if I split my 1000 data points into 100, 100, 100 and I train 10 of them, my first machine will never come to know about the remaining 900 points. Isn't it a loss, right, to the machine? Because machine will not learn varieties of data or the other information present in the remaining 900 data, because it can access only 100 data. Right, so for that, what you do, you repeat this, right? You have a next epoch coming wherein shuffle once again. Okay, you have to shuffle it again and make a subset, in which case you see that you don't get the same 100 points you learned earlier, you will get a different 100. Like that, repeat this. So you will, that's why you go for epochs, right? Repeat this n number of times. Maybe though you have only 1000 points, each time you get 100 points to learn. But if you repeat this process 2000 epochs, definitely every point will come for a larger number of times. Okay, so that is the solution, right? Wherein you will come to know, each of the classifier will actually come to know about each and every data point in your complete data set repeatedly, not only once, because your epochs are 2000. Okay, maybe it will take 10 epochs to come across each and every data point, right? So 2000 by 10, 200. So 200 times it will come to know about each and every data point in a different fashion. So there is a variety coming into picture. Also, you are bringing the randomness in picking up your data points, sampling the data points, etc. will definitely help us in making the machine to understand the problem more clearly, and that's how machine learns. All right. Okay. So these are the important things I want everyone to remember, right? Whenever you build the ensemble, user ensemble learning, right, in future, But now the point comes. I'll try to answer the one question which is asked. This is about obtaining different subset of your data. Okay, so that falls under a specific part of discussion. There is a name for it. It's called as, there are two techniques to obtain these subsets, right? I'll highlight the subsets. So how do you obtain different types of subsets of your data? Two techniques. All right. One is called as bagging, BAGGING. This is one technique. And the second technique is called as the pasting. Okay. Bagging and pasting are the two different techniques. Right. Again, widely used. We will be using this several times, even in our upcoming coding session corresponding to the random forest. Okay. Right. Now you see, let us assume that I am using only decision tree. In order to build the random forest, I have to repeat the decision tree again and again. It's an ensemble of various decision trees, such as 1000 decision trees are going to be used to create what? To create a random forest. Now, definitely, initially I told, if you remember, initially I told that we have to use different data sets given to the each of the each of the trees that are going to be created over here. Otherwise, all the tree will be same. That's of no use. Correct. So what we do? What is our idea? It's an ensemble of various trees. So since the same classifier, what is the same classifier? Decision tree. Since the decision tree itself is repeated 1000 times, I need to create different data given to each of that tree. Correct. So option is, you know that I have to select a subset of data. Don't give the complete data, same data to all at the same time. Take it, make a group of it. Okay, subset of that. So I'll just write one point here because that's what is very important. So I'll just try to put that in one sentence over. Okay, to get the ensemble using the same classifier. Same classifier is in this case because our main topic is still random forest. So random forest is created using decision tree. So same classifier is used to build an ensemble. Correct? So this is what is important for us. If we want to do that, how to do that? So we can train them on multiple, I will write another word. Again, I'll do what is called as randomization. Okay, it's not a multiple subset, it's multiple random subsets. All right, multiple random subsets. Multiple random subset of the training data. Okay, already we know this. I just try to write it in a different way. Okay, now each of these training can be used as a part of your overall ensemble. Okay, so each of whatever these trainings happen, right, with the subset of the complete data set, that is a part of your ensemble. Right, now when you sample, when you create a subset, it's called as a sampling. Out of your whole data set, you are sampling something. Right, now you have basically two options, that are bagging and pasting. Right, so let me try to write in a point. Right, if you try to say I have 1000 data points, I am picking up 100 at a time. Right, again, you know that you cannot do it in order because it says random subset. So I have to pick 100 random numbers out of my 1000. So that will be used to train the first, first machine or the first classifier. Okay, but you may think that what I do, I have already selected 900 are remaining. Out of the remaining 900, pick again 100 at random, train your second classifier, right? This is one option, right? So yes, that is right. So this is called as, this is the sampling without replacement. Correct? Without replacement. I took 100 for the first time. I keep it aside. I train first machine and I keep it aside. I am not using it again. Only 900 remain. So pick up again 100 at random from those 900. Train your second machine. Now only how many remaining? 800 remaining. So out of 800, pick up one more 100 to train your third machine and so on. Right? So this is what is a process. I am not replacing. Whatever I take it from, whatever samples I have taken from my training data set, I am not going to put it back for my next selection. Okay, so that is what is called as sampling without replacement. So this is what is this is what is called as the pasting technique. All right, but there is, people have done research and the research shows that there is another option, that is sampling with the replacement. Okay, so this is what is called as a bagging procedure. So bagging in a sense, for the first classifier out of 1000, I took 100. I train it and I put it back. In the sense, for the next set, when you pick some of the training samples which are used for the first training, right, will definitely come. That's good. Okay, so people have shown that this works much better. Again, a lot of research papers are there, right? If you are interested to go about how they prove this, etc., yes, you should go. Okay, so you should refer, and you will get research papers on that, right? So the how the bagging was invented, how they prove that this is much better than that, etc., you can see. But yes, by doing the research, trial and error, experimentation, people have suggested another method, that is sampling with the replacement provides you much better result compared, because most of them will come to know at least one part of your training data. Maybe out of 100, 10 samples will be common for all of them. That's it. Maybe it may not be 10, less than 10, but still. Okay. So in the next iteration, next 10 data will go as a common one to others, like that. So again, probabilistic way, everything works on the basis of probability. So it is proved that in this technique, if you train the machine, yes, that is that's actually a much more efficient way of sampling. Okay, so that is what is the difference between bagging and paste. Okay, do you have any note with the definition of these two? Please go ahead. Okay, all right. So let me write a few more points here. This is again general. Now, using one of these techniques, you can go for a pasting as well, you can go with a bagging. But as I told, the most standard way that people follow is the bagging itself. Okay, because it has been proved that this actually, right, trains much faster. You can save some time. Even the number of times repetition you need to repeat, number of epochs can be reduced over there. So that ultimately reduces a computational load that you are going to put on your machine. Okay, so because of that, bagging is good. Now, what happens? You select one of this method and you train your machine. Okay, once that is done, next, let us say, okay, let's say all the machines or all the predictors have been trained. Okay, so after after all the predictors or even the estimators. Are trained, a new testing sample can be classified by aggregating the results. After aggregating the results of the Ensemble classifiers members. Okay, aggregation, you know, you can go for a soft voting, hard voting, etc. Out of whatever we have discussed, those are the two methods. But practically speaking, you have many more options, right? That falls under the huge category called as Ensemble, right? So we'll not be touching all of them, but you have some idea now what you should search, at least if you want to know more about this. Okay, all right. So let's take a tea break for 20 minutes, and when we come back, we'll look at the code that is required even for the bagging and some other option. Okay, so please take a break. We'll meet after 20 minutes. Welcome back, everyone. So far, we were discussing about the various types of sampling techniques of our dataset whenever we want to train an ensemble by using same type of classifier. Specifically, when we want to go for a random forest, we need to use the same classifier, that is decision tree. So the options available are pasting and the bagging, and out of which the bagging is going to get a better result. All right. Now let's look at the creation or the coding part that actually incorporates the bagging classifier. All right. So again, this is in sklearn. So first what we do, we have to import the required classifiers. All right. So that is from sklearn.ensemble we import the bagging classifier. Okay, so this is the automatic way of doing the bagging classifier. All right, and anyway, I'll use a decision tree, right? Because decision tree will be used inside the bagging classifier, right? So from sklearn.tree, you have to import the decision tree classifier. So once it is done, you instantiate the bagging classifier. So I'll call bag CLF. This is equal to bagging classifier of, first you have to tell that which function you want to do incorporate here, in the sense which other classifier will be a part of this. So that will be the decision tree. All right. Decision tree classifier, comma. Now you have an option that how many trees you want to create. Okay, so how many trees you want to create, you can use it. That is by using an option called n_estimators. Right? Can keep any number, but as I told, when I have no idea, I will go with the one. Okay, then okay, so again, then what else? What other option I can give? I can give a max samples. Okay, so this is max underscore samples. This is equal to 100. Let me say, in the sense 100 samples are supposed to be collected, right? Out of the complete data set, take 100 data. Okay. Then you will say that do you want to do a bagging or pasting? So that is available in an option that is called as bootstrap. Okay, BOOT. Bootstrap equal to, if you want to perform bagging, then that will be true. Okay, if you keep it false, it performs the paste. All right, then okay, we have one more option that can be used, that is called as the n jobs, n_jobs. We keep it -1. Okay, why? I'll tell you now. So you see, if you have an idea about sklearn, sklearn will not support the GPU computations, right? Why the GPU computation, etc., are required? It is because whenever you go to the deep learning from the machine learning, you will see that the number of computations increase drastically, right? If you are doing 100 calculations right now, in deep learning, it will be 100 to the power 10, something like that. It's a huge increase. So in order to do that by a normal CPU, it's going to take a huge amount of time, because that much calculations our CPUs will not be able to do in a short duration. Okay, so what happens? You will use the GPUs for that, right? Because nowadays every computer has at least a minimum amount of GPU that is available. Since the cost of our GPU came down drastically, each and every system gets, everyone can afford a GPU. Because of that, now the tools such as TensorFlow, Keras, or right, any other tools, right, PyTorch, etc., they support GPU calculation. There is a separate tool. If you simply install TensorFlow, that is normal CPU calculation. TensorFlow GPU is another tool, right, which actually performs the same job done by the normal TensorFlow itself, but on a GPU. If your system has a GPU, it will work on that GPU. Okay, same thing goes with the Keras as well as other libraries. But the scikit-learn what we are using, right, it does not support that. But there is an option that we have, it actually uses all available cores of your CPU. You can enable that. Okay, so if you have multiple cores inside your CPU, right, it can use all. So how to say all? Because I don't know how many are there in my system or your system, because I have to write a general code. General way to represent that all is -1. Okay, all numbers. But if you know that I have 8 cores, I can specify 8. But your system may not have 8, so I don't know how to do that. So the best way to represent that is n_jobs equal to -1. It's going to see how many number of cores are there in your system. It uses everything for that, so that it can increase the speed. So that is a option available in the sklearn. Okay, so that's why the n jobs equal to -1. So once I create this, right, definitely you know how to do that. Now what's the next step? That is bag clf dot fit, correct? I fit the model. So you will pass whatever X train you already have and the Y, whatever Y train you have. Once you have that, the model gets fitted, right? Once it gets fitted, you can go for the testing. So that will be Y predicted. This is what I mentioned earlier. You can go for a prediction as well. So that is bag underscore CLF, or pass only the questions to that. That is X test. So test data will go there. Machine will classify, answer comes in the Y predict. Okay. So after this, definitely you can go ahead and you can create the performance matrix, whatever you require. Okay. So anyway, we'll do that in the actual coding part. All right. So this is the rough code which actually implements the bagging aspect. All right. So starting from beginning, we understood various concepts today, right? What is ensemble, type of ensemble, how to write a code for that. Then we moved ahead and how to form a random forest using the decision trees we saw, and in which the specific type of sampling, the whole data set comes into picture. We called it as the bagging and pasting, out of which the bagging part is there. But if you want to do a pasting, that is also possible. Simply change this true to false. Okay, I'll write all these options. What are the options available here? So there is one thing called N estimators. Okay, you can get a help for this, but still I prefer to write that. So you can see here, whatever we have written inside this part of the code, I'll try to give an explanation for that, because that is pretty much important. Whenever you read this document, you will come to know. Okay, so this is N estimators basically represents the number of classifiers. So if you are using the decision tree, how many decision trees will be created? Like 1,500 or any number that you prefer. Okay, then there is an option called bootstrap. I mentioned that if it is true, if you enter true over there, that is actually for bagging. Okay, if you write false over there, then that is pasting. Okay, then we have another parameter, that is max samples. So what is max samples? Number of samples of the data set, training data set specifically, used for one classifier at a time. Okay, at a given time, I select 100 out of 1,000, or maybe you can change this. All right, then we have the N jobs. This is the number of CPU cores. So that means, and here -1 for all cores or available okay. By default, if you, unless and until you specify all or a number, it will use only one. Okay, that's going to take more time, so it is suggested to use it. That's why specifically I use it. All right. So this classifier is going to use a soft voting scheme itself. All right. Again, anyway, you can look at, if you want to change, definitely there is a possibility. You will just refer and you can check it. Okay, do we have any doubts so far? Whatever we have been discussing so far, if there is any doubt, please go ahead. Okay, that's good. Now we'll have our quiz time. Okay, you can see the questions over here. All right, so all are true false type of questions. So when you type your answer, just write TF, four values I want. That's all. Okay. So TT, TFFF, whatever. Take your time. I'll give us a 3 minutes to think and answer this. Okay, others, please put your answers in the chat box. I'll give, say, 1 more minute to think and answer. Only 5 out of 13 have answered. What about others? Okay, fine. Let's go with the answer. So the first question says that ensemble learning can be used only with the decision trees. Okay, so let me check your answers. One, it says true. Okay, most of you told true, but just look at what is ensemble. Let's go to the beginning. Ensemble, right? Inside the ensemble, you have voting classifier is an ensemble technique, right? And you can see that we have used not only the decision tree, but others have. Okay, so ensemble can be done using any classifier, but when you use only decision trees as ensemble, this creates what is called as a random forest. Okay, so just remember that. Okay, so here the answer becomes equal to false. Okay, next, the bagging involves sampling with the replacement. Okay, so what happens in bagging? Right, sampling with the replacement is bagging, correct? So most of you have given that it's true. Then bagging decision boundary is orthogonal. Okay, so see bagging happens at random, correct? So if look at the orthogonality principle we applied in the decision tree, right? In a decision tree, right, we saw that the decision boundaries are being orthogonal, but here bagging is used, but it does not mean that you have to use only decision tree. You can use any of the schemes over there, right? Ensemble can be done for any of the classifiers. If it is specifically mentioned that decision tree is used for bagging, then the boundary is orthogonal. You can say yes, that is correct. Okay, but here it can be anything. Nothing specifically nothing has been mentioned over here, so this answer becomes equal to false. Okay, then the last one, the voting classifier can be used only with estimators that give probability. Is it true? The first example, right? It just checked out without, if you use a soft voting, then only we calculate the probability, right? Otherwise, there is no question of doing that, right? So it actually, there is a chance of using with the probability. It can also be used without the probability, right? So it says used only with that is false. Okay, so you can use the voting classifier, right, with the ones which do not give any probability out. I hope it is clear. Any doubt with these questions, please go ahead.
Sir, if you, could you repeat the last answer, sir?
Okay, so a voting classifier can be used only with the estimators, so those give probability. In the sense, if there is a probability calculation involved with the what you call classifier, it says that you can use voting only with that. Okay, but that is not true. You can use some of the classifiers which do not deal anything with the probability can also be used under the voting. Okay, so the answer is false.
Okay.
Sure. Yeah. Any other doubt? All right, let's move further. The next concept that we are going to look here is called as, this is also a very important concept, that is called as out of bag evaluation. Now, again, this concept evolved by some of the researchers observing a particular fact during the training, right? Let us assume that we are using the bagging concept for selecting the subset of the data. Okay. Now I know that I have n number of classifiers. For each of the classifier, I use bagging technique to select a subset of my data and I give it for training. Bagging says that, right, you are going to put it back and selecting next subset, training the second one, put the data back, select the next one, do the training for the third method and keep going like that until you finish all of them. Maybe you may have to do it for several epochs. Okay, so let's say that is done. Now, it has been observed that though you are doing the bagging using the random concept, right? You are bringing the randomness into picture. Randomly, you pick up while you create the set of the data set, you do it at random, right? So that is fine for us, right? But again, randomness actually makes the machine to learn much faster than giving it in some order. That's why we have the randomness coming into picture. Okay, now what we do here, okay, people have observed one very important fact, that even after doing the random thing and doing the bagging and right, repeating that for several number of epochs, right, what researchers have observed is that all your data points are still not being used by the machine. Okay, so machine will never come, right, never face each and every data point that is present over there. Some of the data points are still left out because it's random. So whenever I say call it in a loop, right, there is no memory saying that I simply pick up some random numbers. When I select the next random numbers, it does not know what were the previous random numbers created. So it doesn't know whether a particular data point has been used or not. Randomly, it will do that. So by the theory of random numbers, random number generation concept, etc., right, people have come to know that, those who did some research over there, they have proved that no, all the data points are never going to be. So there are some of the data points which are still left out among your training data. So how do you use it is a question. So they have a solution to use that, which is going to lead to a concept called as out of bag evaluation. All right. So hope you understand what it is. I'll try to write it. Right. Meanwhile, if you have any doubt, you ask. All right. So this is actually coming from the bagging. Right. So I'll continue from bagging. In the process of bagging, for say each of the predictor, some of the data points can be sampled multiple times. I already have discussed about it. Some of the points will repeat, right? For the first decision tree, second, third, fifth, 10th, and 15th, everything will get a particular data sample repeated. So something will be repeated again and again. That's what I have written multiple times. Okay, but some are not sampled at all. some of the samples will never be there. So again, this is a note. Okay, I cannot prove it, so that's why I'm writing it as a note. So researchers have proved this. Okay, so in general, only when you have a huge data set also, this is true. Okay, in general, you have lakhs or crores of data points you have with your data set. Again, even in that, when you use a bagging, only the 63% get sampled. So out of 1000, only 630 sample will be used, right, for your training. Though you do bring any randomness or any mathematical technique that is available for you to generate the random numbers, this is what is going to happen. So since you don't have any control over the generation of random numbers, you cannot say that use the remaining whatever 36%, 37%. You don't have a control over it. So 63% of the data set will be sampled out. That means the remaining 37%, right, not sampled, will not get sampled. Okay, so this is a observation, and the mathematicians and the researchers have proved this. Okay, now because of this, the whatever remains unsampled, okay, I'll write unsampled rows are called as, this is out of bag, in short OOB, out of bag instances. Okay, so out of bag instances, whenever somebody uses this word, you should be able to understand that, okay, they have not been used for the training purpose. Okay, now people have come with an idea. Okay, so once they identify a problem, definitely somebody will do a research and come to know that okay, we can definitely come to a solution with that. So anyway, using any of the mathematical technique that is available, it is impossible to make sure that you give the you make machines to use all the 100% of the data. So some will remain as is, right? They will never be used. So you will call it as OOB instances. Okay, so that is out of bag instances. Now the solution they have given is that you try to use them for validation. Okay, so don't create a separate validation data. If you remember, right, what was that concept where you have a complete data set, 80%, 20% you take it, out of the 80%, right, you split it into k different pieces and you do a cross validation, right? Do you remember that? What is the name? Can anybody type the name of that concept where you split your complete training data into k pieces? One of the pieces you keep it aside, right? Remaining you use for training, use it for validation, then repeat it further, right? So fifth one is used for validation, 1 2 3 4 training, then 2 3 4 5 for training, first one for validation, and so on. What is it called? What is the technical name for that?
K-fold.
Yeah, k-fold. What? Correct. K-fold dash. Correct? Yes, please go ahead. Meanwhile, when you think about that, I'll write my next sentence. Okay, so OOB instances can be used for validation instead of creation of a separate validation data set. So if you remember, that is half of what you told is right. It is k-fold cross validation. Okay, validation is to be done by using a validation data set, but you don't have to decide a validation data. Simply say that what is a k number. K equal to 5 means, so first 4 will be training. The last one which remains is a validation data. Then repeat this. So if you have 5 pieces, 5 times this repeats, because every time first 4 I use for training, 1 remains that's going to be used for validation. Then move this further. So these 4 use, this is for validation. Then I separate this out. These 4 will be used for training. This is for validation, and so on. Repeat this 5 times. Your complete data set will be used for the training. One part of it will be used for the validation part. So since the K is what you are going to define, it is called as K-fold cross validation. That's what happened earlier. Now you see that we are supposed to we just have to give a we just have to mention that I want to do something like this. All right. So instead of creating a separate this thing, so once I do the training, I definitely know that which are remaining, because when I finish a loop and I go to the next loop, previous loop is you don't remember, you forget. But when you are inside a loop, you have created 100 random numbers, you know that which are the remaining ones which have not been used. That can be used for the validation, which actually includes your remaining data points, right? So that's what is the concept they have used here, and it works pretty much fine. Okay, so I'll write another point here. In the ensemble itself, we have an option. Okay, ensemble can be evaluated by averaging OOB evaluation of each of the predictors. Okay, so in a code, what is the difference? What makes the difference? I just have to mention one thing. So in scikit-learn, right, we need to set OOB underscore SCORE equal to true. Okay, inside the bagging classifier, we have written an open bracket. We have given many options. In addition, over there, just add one more line to bag. Okay, so that actually solves this problem. Unused data of a particular training process will be used for validation. You don't sorry, you don't have to create a new data. You don't have to split your training data in as a separate validation data. That actually, you see that it's another good thing about it. All right, any doubt with the out of bag evaluation concept?
Excuse me, sir.
Yes, Ruchi, please go ahead.
Yes, sir. Sir, as we know that 37% of the data not get sampled, so it will be automatically taken as the test data by using this oops underscore score.
No, it is not going to be used as a testing data. It is used as a validation. Validation. Okay, automatically taken. Yes.
So how we can separate that data, because we don't know what is that data?
You see, you know what are the random numbers generated, correct?
Okay.
During one iteration, I know these are the random numbers generated. But if I go to the next iteration, these numbers are lost. During an iteration, since you know these are the random numbers generated, remaining are what have not been used, right? That can be used.
So, sir, for out of let us say we have thousands of data set, thousands of records or rows. So, how we can have a look at which is missing or which is not there in my data set?
So
because we are taking the random numbers, na?
Correct. Random numbers are generated. Normally, what happens is that it will take care that what is not generated. Okay, so in a range of numbers, whatever is generated, it uses something like a flag form. Okay, it holds a flag. Okay, this number generated, this is generated, etc. What is not generated will be counted in that order. Okay, what is not there, not flagged out, that's a not generated number. So you can take it out. Okay, and you can use it. So that's how it gets evaluated.
Okay, sir.
Okay. All right. So any other doubt? Okay. Now we'll already we have considered this once, but I will give you another site of what is called as the random forest. Okay, this is ensemble of decision tree using bagging. So if at all I gave this definition at the beginning of the session today, nobody would have understand what is happening here. That's why we took so much time, so many concepts all together to give a proper definition of what is random forest. It is a ensemble learning method. It uses a decision tree. I know what is a decision tree, which uses a concept called as bagging. Okay. Any doubt with this sentence? Please raise a question. Right. I hope it's clear. All right. Now, when it comes to the implementation part, the scikit-learn is the tool which we will be using, because so far we were using that, and that itself is the most suitable what you call library when we start learning something from the towards the machine learning. Okay, so there is okay, inside this particular library we have two options that can be implemented by using the random forest. So the first one is a classifier, right? So I'll just write sklearn. You have the random forest available. Okay, this is divided into two parts. One is a regressor, like the regressor we built in our yesterday session using the decision tree. Okay, same thing, same random forest. Recall, decision tree was used for regression as well as a class. Same thing happens here. You are trying to create a random forest by using n number of decision trees. So the decision tree will be used for a regression as well as the classification. F-I-E-R. Okay, you can do a classifier. Both are available over here. Okay. Now, what exactly is going to happen inside? I'll draw a diagram in some time to explain that. But before that, now, normally what happens is each of the tree will be trained with a random subset. Okay, and you can specify how many samples you want. That is fine. And you also have an option to train with a specific number of what you call samples, and you can also specify, right, what are the features you want to use, because features in the sense the different columns of your data. Okay, so number of columns you have, you can definitely specify what are the number of features you want to specify. In the sense, you can say that I don't want the trees to use all the features available, because if you know, if you see that if you use all the features, maybe your tree can grow, right, larger and larger. So for that reason, there is a hyperparameter. Okay, so you can definitely specify whatever hyperparameters you have been using in the decision tree, even over here. That is definitely valid. Okay, so that is one very important point. So let me try to write a point over here. So that is RF for random forest classifier. The RF classifier can have all the hyperparameters of the decision tree classifier. Okay, so that's how it gets done. Now I'll give you the general architecture of specifically the random forest. Okay, so let's start with a test sample. All right. So test sample is the testing data, one data. Something like I have a photo that is maybe a cat or a dog. All right. So what happens? This data set is given to, I'll draw the trees over here. Let me try to draw a tree. I can use the same tree again and again. So 1, 2, okay. Let me assume that this is a tree. So circular nodes are present. So previously we used to write a rectangular node. For the simplicity, I'm writing this. Okay. So let me try to copy this. Okay. Let's say these are the 3 different trees. All right. And okay, let me try to connect them. So the same sample goes here. This sample itself will go here. And this sample itself will go over here. Okay, so we have this. So this is what I call DT1. This is the decision tree 2. Here we have the decision tree number 3. Okay, you can have any number of classifiers normally, right? Depending upon whatever is your past experience or whenever you referred the references for a particular application, you'll come to know some rough number idea. So each of these classifier will give you a prediction. Prediction 1, prediction 2, the prediction number 3. Okay, maybe these are the predictions that come from any part of the tree. I assume that this is the one which actually gave the prediction, and I assume here this is the one which gave the prediction, and I assume maybe this is the one which gave the prediction. It can come from any point. Then what you do, then you have some aggregation that is coming after this, right? Depending upon what type of averaging you use. Aggregation that actually has to consider all your all the predictions by various trees that are present. Okay, so that comes from the trees this way. Okay, and later on, as a result of this, we get an output. So that output will be the final prediction of random forest prediction. Okay, so that is the overall structure of the random forest. Right now, as I mentioned, right, you can, if at all you are using a single decision tree, maybe you can specify what are the features that are important. Okay, but when you have a huge number of trees present, it maybe it is very difficult to find out what features are really important. Okay, if you leave them to decide, maybe the trees can grow larger and larger, right? So Otherwise, if you put a restriction in terms of the number of depth, right, maybe some of the features may miss out. Okay, so to overcome this problem, all right, so I'll go to a particular topic that is actually called as the feature importance.
Sir, please some roll up
Yeah, sure.
table. Some one last heading. The test sample के ऊपर का.
Last
no,
one. Okay, okay.
no,
Previous to this,
oh.
sure.
No, but yes, correct. Sir, table. Test sample. Yes, thank you, sir.
Okay, sure.
Yes.
All right. So now we are trying to decide what are the features are pretty much important, right? So because random forests are, you can use a random forest for evaluation of the important features, which are in my data set, which are the really important features you can try to find out by using this random forest as well. But how to do that? What we do, this is the procedure to do that, right? First, we'll consider all the nodes of all the decision trees in our forest, okay, in the random forest that use a particular feature. Maybe I'm looking for the first feature, whether it is important or not. So I'll consider all the nodes in all the trees of the forest which uses that as a feature, okay, that use a particular feature, right? Then you are going to measure the impurity present over there, right? What's the name of the impurity? It's right. Do you remember the name of the impurity? What was the specific name? Anybody? Please type your answer in the chat. Okay. Measure how much impurity is reduced by splitting on that feature, because every node will split. Okay, what's the name of the impurity? It is Guinea impurity, right? You have an equation also for that. Okay, so try to go back to the decision tree if you have any doubts or anything you want to recall about it. So at every node you have node splits into two branches, and the splitting happens because of the impurity present at that node. So how much that impurity is reduced by splitting that into two parts, you will try to find out over there. Okay, then you have this happening for all the trees. What you do, you try to take an average of that value. Okay, so take the weighted average, where weights of the number of training samples are associated with each of them. Okay, so take average, weighted average of this value which you have calculated. Now you are going to find out a score which you can call it as an importance score. All right, so I'll write scale the, that is the weighted average value you get itself is called as a importance score. Okay, so scale the importance score to sum it up. So you have done for one particular feature. Repeat this for all the features. So if you want to know what are the top 10 features, find out this scaled weighted value for all the features and take top 10. So those are the top 10 features which you have to consider. if you want to find out the top, if your data set has say 50 columns and you want to find out what are the top 20 columns out of it, you can do the same thing, and you can find out what are the top 20 features of it, top 20 values, right? You get. So like that, you can try to find out the important features in your data set. Okay. All right. Do we have any doubt with this? Anyway, there is a coding part that comes into picture. So I'll just give a code, right? Not the complete code. I'll just give a sklearn, right? In sklearn, we have to use if it's a random forest, right? So I'll use rf random forest clf. This is my function dot feature a importance ces underscore. Okay, so this is the particular command which is going to help you out in finding out the important. So normally what happens if you have so normally I don't suggest you to go with the top 10, top 20 or something. You see all of them, and with the percentage value you get, like this is 40% importance, this is 10% important, the next feature 15% important, like that you get a score. Okay, that's what I will show you when we do the coding part. So just to remember which is the function that is used, you can see this. Okay, so this is the particular function. So normally here this rf underscore clf is what is the name I have given to my random forest classifier. So dot after that, whatever you have written, feature underscore importances, CES is there. Okay, underscore. That is the particular function which actually talks about the important features of your random forest. So we will be able to see the importance over there, right? I'll when we do the coding, definitely we'll be seeing that as well. All right, then. Yeah, I think I have covered most of them. Let me check whether we left anything out of it or